Welcome. Today, we're diving into the fascinating world of recurrent neural networks, or RNNs, and their pivotal role in natural language processing, often called NLP. RNNs are a special type of neural network designed to handle sequential data, making them perfect for language-related tasks. Unlike traditional neural networks, RNNs have loops that allow information to persist, which is crucial for understanding context in language. In this video, we'll explore how RNNs work, why they're so effective for NLP, and look at some real-world applications. Let's start by understanding what makes RNNs unique compared to other neural networks. Appreciate RNNs, it's important to grasp the idea of sequential data. In language, words and sentences follow a specific order, and meaning often depends on what came before. For example, the word bank could mean a financial institution or the side of a river, depending on the context. RNNs are built to process this kind of data where the sequence matters. They remember previous inputs, allowing them to make sense of language in a way that traditional neural networks can't. This ability to handle sequences is what sets RNNs apart and makes them so valuable in NLP. So how do RNNs actually work? At their core, RNNs process one element of a sequence at a time, maintaining a hidden state that carries information from previous steps. This hidden state acts like a memory, helping the network understand the context of the current input. As each word or character is processed, the RNN updates its hidden state, allowing it to remember important details from earlier in the sequence. This mechanism is what enables RNNs to excel at tasks where order and context are key, such as language modeling and translation. Traditional neural networks, like feed-forward networks, process inputs independently, without considering the order. This works well for tasks where context isn't important but falls short for language. RNNs, on the other hand, are designed to handle sequences, making them much better suited for NLP. By maintaining a hidden state, RNNs can use information from earlier in the sequence to inform their prediction. This fundamental difference is why RNNs have become so popular in language processing tasks. One of the most common applications of RNNs in NLP is language modeling. Language models predict the next word in a sentence based on the words that came before. For example, given the phrase "the cat sat on the," a language model might predict "mat" as the next word. RNNs excel at this task because they can remember the context of the sentence, allowing them to make more accurate predictions. This capability is essential for many NLP applications, from text generation to speech recognition. RNNs are also widely used for text generation. By training on large amounts of text, an RNN can learn to generate new sentences that mimic the style and structure of the training data. This is how some AI-powered chatbots and creative writing tools work. The RNN takes a starting phrase and predicts one word at a time, using its memory of previous words to create coherent and contextually appropriate sentences. This ability to generate human-like text has opened up exciting possibilities in content creation and entertainment. Another powerful application of RNNs is in speech recognition. When you speak to a virtual assistant, RNNs help convert your spoken words into text. Speech is naturally sequential, with each sound depending on the ones before it. RNNs process the audio signal one frame at a time, using their memory to understand the context and accurately transcribe speech. This technology is behind many voice-controlled devices and services we use every day. RNNs have revolutionized machine translation, enabling computers to translate text from one language to another. By processing sentences word by word and remembering the context, RNNs can produce translations that are much more accurate and natural-sounding than earlier methods. This is especially important for languages with different word orders or complex grammar. RNN-based translation systems have made it easier for people around the world to communicate and access information in different languages. Sentiment analysis is another area where RNNs shine. This task involves determining the emotional tone of a piece of text, such as whether a review is positive or negative. RNNs can analyze the sequence of words and understand subtle cues that indicate sentiment. For example, the phrase "not bad at all" has a positive meaning, even though it contains the word bad. By considering the context, RNNs can make more accurate predictions about sentiment, which is valuable for businesses and researchers alike. Named entity recognition, or NER, is a key NLP task where RNNs are often used. NER involves identifying and classifying names of people, places, organizations, and other entities in text. For instance, in the sentence "Apple released a new iPhone in California," NER would recognize Apple as a company and California as a location. RNNs help by processing the sentence in order and using context to accurately identify entities, even when names are ambiguous. Out-of-speech tagging is the process of labeling each word in a sentence with its grammatical role, such as noun, verb, or adjective. RNNs are well suited for this task because they can consider the context of each word within the sentence. For example, the word "run" can be a noun or a verb depending on the surrounding words. By analyzing the sequence, RNNs can accurately assign the correct tags, which is essential for deeper language understanding. Text summarization is another exciting application of RNNs. Here, the goal is to generate a concise summary of a longer document or article. RNNs process the text sequentially, identifying the most important points and generating a summary that captures the main ideas. This is incredibly useful for quickly understanding large volumes of information, such as news articles or research papers, and is increasingly used in digital assistants and news aggregators. RNNs are also at the heart of many question-answering systems. These systems read a passage of text and answer questions about it, much like a human would. RNNs process the passage and the question, using their memory to find relevant information and generate accurate answers. This technology powers virtual assistants, search engines, and educational tools, making it easier to find information quickly and efficiently. Despite their strengths, RNNs face some challenges. One major issue is the vanishing gradient problem, where the network has trouble learning long-range dependencies. This means that as sequences get longer, it becomes harder for the RNN to remember information from the beginning. Researchers have developed advanced RNN architectures like LSTMs and GRUs to address these issues and improve performance on complex language tasks. Long short-term memory networks, or LSTMs, are a special type of RNN designed to overcome the vanishing gradient problem. LSTMs use gates to control the flow of information, allowing them to remember important details for longer periods. This makes them especially effective for tasks that require understanding long sequences, such as document classification or language translation. LSTMs have become a standard tool in NLP, thanks to their ability to capture complex patterns in language. Aided recurrent units, or GRUs, are another advanced RNN architecture. Like LSTMs, GRUs use gating mechanisms to manage memory, but with a simpler structure. This makes them faster to train and easier to implement, while still providing strong performance on many NLP tasks. GRUs are often used when computational efficiency is important, and they have become a popular choice for real-time language application. Bidirectional RNNs are an extension of standard RNNs that process sequences in both directions, forward and backward. This allows the network to use information from both the past and the future, leading to better understanding of context. Bidirectional RNNs are especially useful for tasks like named entity recognition and sentiment analysis, where context from both sides of a word can improve accuracy. Attention mechanisms have further enhanced the capabilities of RNNs in NLP. Attention allows the network to focus on specific parts of the input sequence when making predictions, rather than treating all inputs equally. This is particularly useful in tasks like translation, where certain words in the source sentence are more relevant to the translation than others. Attention has paved the way for even more advanced models, such as transformers. RNNs are a core component of many modern chatbots. By processing user input sequentially and maintaining context, RNNs enable chatbots to generate relevant and coherent responses. This makes conversations feel more natural and engaging. Whether it's customer support or virtual companions, RNN-powered chatbots are becoming increasingly common in our digital lives. Text classification is the task of assigning categories to text, such as spam detection or topic labeling. RNNs analyze the sequence of words in a document, using their memory to capture important patterns. This allows them to accurately classify text based on its content, even when the meaning depends on context. RNN-based classifiers are widely used in email filtering, content moderation, and information retrieval. Sequence labeling is a broad category of NLP tasks where each element in a sequence is assigned a label. Examples include part-of-speech tagging and named entity recognition. RNNs are ideal for these tasks because they can consider the entire sequence when making predictions, leading to more accurate and consistent labeling. This is crucial for building reliable NLP systems. Sequence-to-sequence, or sec-to-sec, models are a powerful application of RNNs. These models take an input sequence and generate an output sequence, which is essential for tasks like translation and summarization. Sec-to-sec models use two RNNs, an encoder to process the input and a decoder to generate the output. This architecture allows for flexible and effective handling of complex language tasks. RNNs are also used in spell checking and correction systems. By analyzing the sequence of characters or words, RNNs can detect and correct spelling errors in real time. This is especially useful in mobile keyboards and word processors, where accurate and fast correction improves the user experience. RNN-based spell checkers can even suggest contextually appropriate corrections, making them smarter than traditional rule-based systems. Autocomplete features in search engines and messaging apps often rely on RNNs. By predicting the next word or phrase as you type, RNNs help speed up communication and reduce typing effort. These systems use the context of what you've already written to make intelligent suggestions, making them more helpful and accurate than simple dictionary-based approaches. Recommendation systems, such as those used by streaming services and online stores, can benefit from RNNs. By analyzing the sequence of user interactions, RNNs can predict what content or products a user might be interested in next. This sequential approach allows for more personalized and relevant recommendations, enhancing the user experience and increasing engagement. Handwriting recognition is another area where RNNs excel. By processing the sequence of pen strokes or characters, RNNs can accurately convert handwritten text into digital form. This technology is used in note-taking apps and digital signature verification, making it easier to digitize and process handwritten information. Although our focus is NLP, it's worth noting that RNNs are also used for time series analysis. In NLP, this can mean analyzing sequences of events or actions described in text. RNNs can model patterns over time, making them useful for tasks like event prediction or trend analysis based on textual data. Dialogue systems, such as those used in customer service bots, rely heavily on RNNs. These systems must understand and generate responses based on the entire conversation history. RNNs are ideal for this because they can remember previous exchanges and maintain context, resulting in more coherent and helpful interactions. Information extraction involves pulling structured data from unstructured text, such as extracting dates, names, or locations from documents. RNNs process the text sequentially, using context to accurately identify and extract relevant information. This is crucial for building databases from large volumes of text and automating data entry tasks. Text normalization is the process of converting text into a standard format, such as expanding abbreviations or correcting capitalization. RNNs can learn to perform these transformations by analyzing the sequence of characters or words. This is especially useful in preprocessing text for other NLP tasks, ensuring consistency and improving downstream performance. RNNs aren't limited to natural language, they're also used for modeling programming languages. By analyzing sequences of code, RNNs can predict the next token or suggest code completions, aiding developers in writing software. This application is becoming increasingly important in modern development environments and code editors. Plagiarism detection systems can use RNNs to analyze the sequence of words and phrases in documents, identifying similarities and potential copied content. By considering the context and order of words, RNNs can detect subtle forms of plagiarism that rule-based systems might miss, making them valuable tools in education and publishing. Text-to-speech systems convert written text into spoken words, and RNNs play a key role in making the speech sound natural. By modeling the sequence of phonemes and prosody, RNNs help generate smooth and expressive speech, improving the quality of virtual assistants and accessibility tools. Language detection systems use RNNs to analyze the sequence of words or characters in a text and determine which language it's written in. This is important for multilingual platforms and translation services, ensuring that content is processed and displayed correctly for users around the world. Grammar checking tools use RNNs to analyze the structure of sentences and identify grammatical errors. By considering the sequence and context of words, RNNs can detect mistakes that simple rule-based systems might overlook, providing more accurate and helpful feedback to writers. Paraphrase detection involves determining whether two sentences have the same meaning, even if they use different words. RNNs can compare the sequences and context of both sentences, making it easier to identify paraphrases. This is useful in search engines, plagiarism detection, and question-answering systems. Dialogue generation is the process of creating responses in a conversation, and RNNs are often used for this purpose. By analyzing the sequence of previous messages, RNNs can generate relevant and coherent replies, making conversations with AI systems feel more natural and engaging. Coreference resolution is the task of determining which words in a text refer to the same entity, such as linking he to John. RNNs process the sequence of words, using context to accurately resolve references. This is important for understanding the meaning of complex sentences and improving the performance of NLP systems. Document classification involves assigning categories to entire documents, such as sorting emails into folders or labeling news articles by topic. RNNs analyze the sequence of words throughout the document, capturing the overall meaning and context. This leads to more accurate and reliable classification, especially for long or complex texts. Topic modeling is the process of discovering the main themes or topics in a collection of documents. RNNs can analyze the sequence of words and identify patterns that indicate different topics. This is useful for organizing large datasets, improving search, and gaining insights from text data. Fake news detection systems use RNNs to analyze the sequence and context of words in news articles, identifying patterns that may indicate misinformation. By considering the structure and flow of the text, RNNs can help flag suspicious content and support efforts to combat the spread of false information. Text mining involves extracting useful information from large volumes of text data. RNNs can process documents sequentially, identifying trends, relationships, and key insights. This is valuable for businesses, researchers, and analysts who need to make sense of unstructured data. Social media platforms generate massive amounts of text data every day. RNNs are used to analyze posts, comments, and messages, identifying trends, sentiment, and emerging topics. This helps companies monitor brand reputation, track public opinion, and respond to customer feedback in real time. Future of RNNs in NLP looks promising, with ongoing research leading to even more powerful models and applications. While newer architectures like transformers are gaining popularity, RNNs continue to play a vital role in many systems, especially where sequential processing is essential. As technology advances, we can expect RNNs to become even more efficient and effective, opening up new possibilities for language understanding and communication. Wrap up: recurrent neural networks have transformed the field of natural language processing by enabling computers to understand and generate human language in a way that was previously impossible. From language modeling and translation to sentiment analysis and chatbots, RNNs power many of the tools we use every day. While challenges remain, ongoing innovations continue to expand their capabilities. Understanding RNNs is key to appreciating the incredible progress in NLP and the exciting future ahead.